Okay, hey folks, we are getting into Module 4 on the second and third laws of thermodynamics. It will be a fairly large module, as you can see, 13 learning goals there. So we'll spend a couple weeks here, just like we did with the previous module. And on this first learning goal, we're going to set up the definition for the second law of thermodynamics. So I love this picture here to describe what the second law of thermodynamics is getting into. So this picture is in our Atkins text. So imagine here that we've got this bouncy ball and we let the bouncy ball go, and our common everyday experience will tell us that it will spontaneously bounce until it's run out of its kinetic energy and will eventually end up on the floor somewhere and perhaps roll away. So when we want to start thinking about this in the context of the second law, we have to ask the question, is this reversible? Okay, and let's kind of work out what would have to happen to make this process reversible. So we have to imagine now our ball is sitting somewhere on the ground, and all of this dispersed energy, right? So each time the ball hits the ground, it disperses some of its kinetic energy into the ground. Well, to reverse this, we would have to focus all of that dispersed energy into one single point, perhaps by allowing the atoms in the ground to vibrate in some very focused way, which might cause the ball to start to vibrate enough that it can bounce. And then when it goes to its second bounce, we would have to focus even more energy into one spot to make it bounce even higher, and so on and so forth. I can tell you with confidence that no one has ever observed this in the history of the universe. So the answer to that question is no. And now we can begin to use this picture to understand what the second law of thermodynamics is getting into. Spontaneous changes, spontaneous, are always accompanied by a dispersal of energy, right? So as this ball bounces in the forward direction in the usual way, it disperses its energy out into the ground each time. And to reverse that would require us to go against this notion of energy dispersal. So here's another way we can view the second law, which is more related to engineering, and we will get into those details in this class. So the Kelvin statement of the second law says, no machine can exist which perfectly converts heat into work. So now let's imagine we've got our machine here that's taking some hot source, and I'll call this thing our system, and everything outside of that is the surroundings, where on first inspection, this seems like a totally legit machine. We've got a hot source. It's providing that heat into an engine, which can convert that heat into work. So what's the issue? Well, the issue is when we have a hot object in contact with a cold object, like the surroundings, heat will flow spontaneously from a hot object to a cold object, and it does it in this dispersed way as I'm drawing. So to think that we could focus the heat into one singular direction and convert all of that heat into work perfectly is about the same thing as suggesting that we could focus all of the energy of the atoms in the ground to make this bouncy ball bounce in reverse. So these pictures are actually one and the same, even though it might not appear that way. So in other words, we can't use all of that heat for work. So not all heat can be used for work. So some of it must be lost to the surroundings to satisfy the second law. So, and here is our statement of the second law in a more concise way, or in a more exact or precise way, I should say. The entropy of an isolated system increases in the due course of a spontaneous change. Thermodynamically, irreversible processes are spontaneous and hence must be accompanied by a dispersal of energy and an increase in total entropy. Okay? So here is that same statement written in math. And oftentimes we'll see this written as delta S universe. I like saying total because I think when you say delta S universe, to me it gives you this impression that we're talking about some big, grand thing. And perhaps we are, but more likely we might just be talking about like a chemical reaction occurring in a beaker. And we could still then consider that as the total entropy when thinking that that's the change in entropy of the system plus the change in entropy of the surroundings. So you might see this written as universe in other texts. I like saying total. And then, of course, for that process to be spontaneous, this sum must be positive. Okay? So we could have a reduction of entropy in the system and still have a spontaneous process. So, for example, if delta S system is negative, then our process could still be spontaneous as long as the following happens. Then that means the absolute value of the entropy change of the surroundings must be greater than the absolute value of the entropy change of the system, right? So if delta S system is negative, as long as delta S surroundings are more positive than delta S system is negative, our process is still spontaneous, okay? Of course, we could also have a delta S of the surroundings being negative, and to have a spontaneous process, the same thing must apply. So in this case, then, the absolute value of the entropy change of the system must be greater than the absolute value of the entropy change of the surroundings, such that when we add them together, we get an overall positive quantity. Now, this doesn't have to mean that all processes have a delta S total greater than 0. So if delta S total is less than 0, then our process is not spontaneous, okay? Then not spontaneous, okay? And we will continue to explore this idea of spontaneity and entropy changes throughout the rest of this module. All right, I'll see you in the next video.